Hello everyone, we are group C019 and our topic for this exposition is SymPy Combinatorics. SymPy is a powerful Python module which is used for symbolic mathematics. It helps to solve problems related to permutation, combination, partition and many more. We have shown 4 practical applications in our website. Through this project, we explored the important uses of this library with code example and real-world applications. The first topic in SymPy is partition, which means dividing something into parts. In set theory, a partition is a collection of disjoint sets whose union equals a universal set. Let's take an example. Imagine a teacher has 6 students and wants to divide them into study groups based on their subject preferences. Each student belongs to exactly one group as shown. We can solve this problem using partition. First, we need to learn about restricted growth strings. In RGS, a list of numbers is given where each number indicates which subset the ith element belongs to. For example underscore RGS dot members returns a sorted tuple, while dot RGS prints a tuple of indices, showing which student belongs to which group. Using this, we can quickly answer question 1, identifying students in each group. So here's the code. Similarly, we have some other properties like partition, rank, and conjugate. Now moving on to subsets. They are generated using simple binary manipulation. These are the various code examples for it. The next one is the gray code. Gray code is a way of listing all possible subsets so that each new subset differs from the previous one by adding or removing just one element. Now let's talk about permutation. It is a way of arranging a set of elements where order matters. In SymPy, the permutation class helps create and work with this arrangement. For example, if we apply a permutation and get 0 to 1 as output, it means index 0 moves to index 2 moves to index 1, and index 1 moves back to 0, which forms a cycle. Similarly, we can rearrange a list like ABC into BCA using the permutation 201. Permutation have key properties. The first is identity, which does nothing and keeps the original order, which we can verify using code. Inverse permutation restores elements to their original position. The next one is order, which tells us how many times we must apply a permutation to return to the original arrangement. Parity helps check if a permutation is even or odd based on the swaps. For an odd number of swaps, the output is false. For even, it is true. Lastly, cyclic decomposition breaks a permutation into smaller cycles where elements move among themselves. Now let's talk about permutation group, which are collection of multiple permutation following certain rules. Key properties include identity operation, which keeps elements in a place, and next is order, which counts distinct elements in the group. Then we have generate method that lists all possible permutation, and the last is permutation check, with which we can check if a specific permutation belongs to a group or not. In conclusion, we have included practical application as well. One example is that of data encryption, where the position of letters in a message are changed using a set pattern. For instance, with permutation 42031, the word hello turns into OLHLE. In a similar way, smart homes use subsets to track which devices light, fans, TV or AC are on. Python subset function helps find the next on combination. If the TV and AC are on, the next step might be turning on only the fan. This makes home automation more efficient. Permutation groups are also useful in chemistry, where they help in identifying molecular symmetry. In AI and machine learning, permutation groups are important too. A great example is that of AlphaZero, which is a chess engine which uses group-based search. By using generate method, it can list all possible moves, helping in system making better decisions. Through this, we explored SymPy Combinatorics module, showing its power in permutation and real-world application. Thank you.